Hello and welcome back. So, in this applications week we will look at an application of deep neural networks, specifically CNNs, and a combination of machine learning classification algorithms to a problem in medical imaging or medical image analysis. So, this is based on a paper out of our lab which appeared in medical image analysis titled Fully Convolutional Multiscale Residual DenseNets for Cardiac Segmentation and Automatic Cardiac Diagnosis using an ensemble of classifiers. Okay. So, my PhD students are co-authors in this paper along with me, okay, Varghese and Mahindra Kenneth. Mahindra will actually walk you through some of the code and some pieces of this algorithm later on. I will just give you an overview right now. Okay, this is the outline of what you are going to look at. So, we will just give you an introduction to and motivation to this particular problem, because you might not be aware of what medical imaging techniques are and what they are used for, etc. And then the proposed methodology is segmentation pipeline, and the rest about diagnosis of the pipeline and the code walkthrough and some aspects of the data will be done by Mahindra. Okay. So, let us go to the introduction. So, if you are all familiar with magnetic resonance imaging, if not, you just look it up on the web, there are some resources. The physics of how it operates, it is an entire course by itself, but we will just see for the sake of this slides, you can just look at what it is used for. So, magnetic resonance imaging is one of the main tools for assessment of cardiac function. Okay. Cardiac function means function of your heart. Okay. And it is also considered a much more reliable method, and people use that in the clinic. That is, if you go to a hospital and they take an MRI of your heart, they can use that to figure out if there is something wrong with the function of your heart. Okay. So, let us see what MRI does. So, what many of the modern imaging techniques do, it is take a CAT scan, or in this case the MRI scan, it gives you sections of your anatomy. Okay. So, if you all recall, if you go to a hospital, you lie down on a flat bed and then the bed moves into the gantry, and you lie there for some time while the image is acquired. So, it is like it slices your they acquire slices of images that run through your cross sections of your body. Okay. So, these are referred to typically as axial slices. MR is slightly more flexible, it can acquire images at random cuts. So, you can make a cut like this and look at the cross section of your anatomy. Okay. So, for the purpose of this particular paper, we are going to only look at the cardiac imaging planes. Also urge you to look up some 3D model of the heart. Lots of anatomical atlases available online, but for this lecture just concentrate on this one. We typically acquire a volume of the heart. So, your entire organ is covered by the scan. So, slices through the heart are acquired, and the way we slice the notation is important. So, if you look here, what is regarded as the LV is the left ventricle. The left ventricle is the chamber in the heart that pumps out blood into your system. Okay, through the aorta, that is where the nutrient enriched blood comes out of your heart. And if you cut and from LV, if you try, it looks like kind of like an oval if you think about it, and if you cut across its short axis, those image sections are known as short axis images. And there are the long axis planes which cuts through the section of the heart, the entire section. So, think of it like cutting this way, okay, as opposed to a short axis which cuts this way, right. And the other plane is the 4-chamber plane, which is basically the plane which will show you all compartments of the heart. The heart has 4 compartments or 4 chambers: right ventricle, right atrium and left atrium. So, if you want a view that has all the 4 chambers, cross sections of all the 4 chambers in it, that is called the 4-chamber plane. Okay. So, typically these are the 3 orientation at which the volume of the heart is viewed. So, you can think of the image acquired as a volume. Volume is a 3D matrix. Okay. It is a grid, 3D grid, and where it is pixelized, of course, because it is a reconstructed image, the acquisition is discrete. Okay. The sampling is discrete. So, you will get a discretized image, 3D discretized image, and you can look at each plane of the 3D volume as belonging to either the short axis, long axis, or the 4-chamber plane. Okay. So, we will be primarily working with the short axis plane. So, we will see what that looks like. Okay. So, here is a picture of the an animation of the short axis view. If you look at this, so this is the compartment into which the blood actually goes through. The dark region here, that is called the myocardium. Okay. That is the myocardium is the muscle. Okay. The muscle which actually twists and compresses the heart, you can think of it that way, and pumps the blood out of the into the system. Okay. So, this is if you acquire the images of a beating heart, remember the heart is not a stationary organ, and since magnetic resonance imaging helps you acquire images very quickly, you can actually acquire a heartbeat. The sense you can at least sample different heartbeats at specific time intervals and put together this image. So, the entire one heartbeat is one cardiac cycle, like compression and then release, that is acquired during when the that entire stroke, one stroke of the heart, which is like it pumps the blood out, that is called one cardiac cycle, and images are acquired throughout the cardiac cycle. So, you have volumes of, let us say, for instance, if a typical heartbeat is 1 second, you can end up acquiring 20 or 20 to 25 time points in that 1 second. Okay. At each second you will have the heart in a different state of compression or expansion in one cardiac cycle. Okay. You can think of it that way. So, this plane on the left that you are looking at, this is the axial plane. Okay. You can see the cross section, this is a short axis cross section. Okay. The 4-chamber view is right there, again the left ventricular long axis is shown right there, and this shows all 4 compartments. You can see the heart, the section of the heart where all 4, where because the blood travels through all the 4 compartments before it gets pumped out of the system. Okay. And so, that is the 4-chamber view right there, and this is the long axis view where you can see the along the length of the left ventricle, if you can think of it that way. So, typically for all these cardiac MR imaging, so there are many diagnoses that are done with cardiac MRI, but what is of most interest to clinicians, many clinically important factors are obtained by looking at the left ventricle, because that is the one that pumps blood out into your system, and any weakness there or any defects or pathology there is obtained by studying the left ventricle during the cardiac cycle, how when it pumps blood out. Okay. So, another terminology that you should be aware of is called the systole and diastole. So, think of the diastole as when the left ventricle is filled with the blood, that is when the myocardium, let us say, is relaxed a little bit and it fills the blood, and that is the diastole. The systole is when it is fully compressed, that is when it is actually pumping it out into the system. So, these are the two, and images are acquired between end systole and end diastole, that is typically the terminology that is used. So, just to reiterate, if let us say if your heartbeat is 60 beats per minute, so you have 1 beat per second, which corresponds to pumping out once, so one pumping action. So, there are typically 20 to 30 image volumes, the entire volume of the heart is acquired between that 1 second. So, that gives you, like, so if you run it like a movie, that is what you will get. If you put together, if you take a particular cross section of the heart and you take the same cross section from every time point image and put it together, you can make a movie like this. That is how this is done. There are some other terminologies, and again just a better view of the heart. So, here you can see the base of the heart is basically, if you can think of it, is the top of the heart. So, when you are standing up, that is where the base is, and the apex is that tip right there. So, that is how you would the direction, if you think of it, the base to apex or apex to base is how it is referred to as. Okay. And just coming and continuing from the previous slide, if you look, we have this region in green which is referred to as the myocardium. Myocardium is the muscle that does the pumping. Okay. So, whenever there is something wrong with that muscle, that is when you get all these heart problems like heart attack or cardiac arrest, things of that sort. The left ventricle is the cavity which contains the blood. Okay. And the right next to it is the adjacent chamber is the right ventricle, again highlighted in green. So, if you go back to the previous slide, I think, so if you look at this this particular slice here, we can see the LV very clearly. This is just the left ventricular zone. So, and if you look at this slice right there, that's where the this is the left ventricle, as I point out. Right next to it is the right ventricle, that is the region. I will just mark it just to show you. So, I am not an expert in anatomy, I have just learned some of it in the context of this problem. Okay. So, you should if possible consult some radiologist or somebody who you know is a medical student or somebody who has done medicine. He can probably point this out way better than I can, but in the context of the problem, these are the anatomies that we will be concerned with. So, this dark region that you see, I will use a different color, maybe I will use green as in the other one. So, this dark region here, which I am going to shade, that is where the myocardial muscles are. Those are the muscle, that is the muscle region which pumps your blood out of your system. Okay. Okay, so that's been highlighted here. The left ventricle is a cavity that holds the blood, the surrounding muscle, that's a myocardium, and the adjacent chamber is called the right ventricle. Okay. Okay, so before we go any further, so what is the challenge? Okay, so what are we going to do? So a lot of times when the patient is imaged, the doctors can just, the radiologist can just go through these images and can see defects sometimes. A lot of times some quantitative analysis has to be done. So one of the things, several factors that are calculated are the ejection fraction. Okay, if you want to look at the area of the myocardium, or size of the myocardium, and also for all of those tasks where you need some quantitative markers to be obtained from the image, what you need is an accurate segmentation. So this is what we use, what we call semantic segmentation when we looked at convolutional neural networks. So basically we have to label the pixels corresponding to the myocardium, label the pixels corresponding to the left ventricle, and label the pixels corresponding to the right ventricle. Okay. So these things have to be accomplished automatically. So why is this so important to do automatically? Why can't just the radiologist go ahead and do it? So the problem is there will be many volumes in time. So we talked about that. So but even if we considered volumes acquired at end systole and end diastole, that is when the end diastole is when the like you can think of the left ventricle as being filled with blood, and end systole is when it's pumped out. Okay. So if you look at it, so each volume will have hundreds of slices. Okay. Each volume will have hundreds of slices, and if you are also going to go through several time points, then it means that you are going to have to look at about 1,000 slices of information, 1,000 pictures if you want to put it that way, 1,000 pictures in which the radiologist has to go and manually mark these boundaries, and that is going to be prone to error, and it is definitely going to be time consuming. I do not think we can radiologist can see more than a patient a day if that is the case. Okay. So if in that case, so an automatic technique for figuring out this out is essential for doing the segmentation, right. So that is one thing. The second, the important thing is, what do we do with all these quantitative measurements, right? What do we do with it? The idea is to predict disease. Okay. So a patient walks in, maybe is being referred to by some doctor, by some cardiac specialist, that maybe you should have your heart scanned by MRI. So he does the scan and the volume image comes out. So okay, then maybe it is nice if you have a system that provides a diagnosis on its own, like what kind of, there are several conditions, we will see what those conditions are. There are, in this case we are considering I think 4 conditions, 4 to 5 conditions which can be actually inferred from the images themselves. Can we do it automatically? So that is the question. So for instance, this is like saying, if you look at the do a whole body patient scan of the patient and say, oh, you have cancer, right, something like that, some diagnosis like that, without having to without manual intervention, right. So that is the idea. So there are twofold, one is the automatic semantic segmentation as we know it, the second is prediction of the disease in the heart based on the quantitative markers or values that we obtain from the segmentation. Okay. We will see what those values are later on in the task, but that is the thing. Okay. So what is the pipeline for this work? Okay. So generally this has we have about I think 3 blocks. Okay. So the first one right here, that is the one we are going to look at, that is the pre-processing. Okay. It contains everything that some of the aspects of data normalization also is contained in that. So we will see what this pre-processing technique exactly is. So the pre-processing helps us to actually zoom in on the region in the image that is of importance to us. So why would that be important? So if you look at the picture here, you can see there is it is a pretty big image I think, right, and it is about 512 by 512, it can vary from 256 cross 256 to 512 by 512. If you look at it, only a small region here, this is the region of interest for us. Okay. This is where the heart is, cardiac muscles are, and only we need only this region. Okay. So to make our CNN's job easier, so we do not want a very large input to our CNN, if you can just crop this region out in every image successfully and automatically, that will be useful. Okay. So then that is what this particular piece does. The second piece, again data normalization kind of seeped in here because it is part of the training process I guess in the neural network. So we have a neural network portion here. So that is our deep CNN, you can call it. Okay. And the output is the segmentation. We do some post processing of the segmentation masks just to make sure they are clean. The third place is here is a classification of disease. Okay. So, these are the 3 steps. So, we will go through each one of them. I will give you a brief overview and then we will see that some what the individual steps are in much more detail. Okay. So, the region of interest extraction, okay, that is step 1. So, how is this accomplished, right. So, I mentioned to you that when if you have, let us say if you have 60 beats per minute, that is your heart rate. So, you get about in a second you have 1 beat is completed, and then we acquire about 23 or 20 to 30 volumes in that 1 beat, right, that is the entire volume. So, then that is useful because if we consider the same plane, the same height, same cross section in every one of those time points, let us say. So, for instance, we acquire m equal to 30 time points, which corresponds to 30 volumes. Okay. We select a plane. The scanner has some references, so then we will be able to figure out in actually absolute terms where a particular z value lies, where a particular coordinate lies. So, we should be able to select that plane, and if you arrange that plane in the time series, that is what this is going to, so it is seen as a cardiac phase. So, different stages of compression or expansion of the heart is referred to as the cardiac phase. So, if you arrange them, you see then we get a stack of images and we can take a standard deviation across that stack. So, you can arrange them as a stack, and if you take 1 pixel, you can look at that pixel through the stack and calculate a standard deviation. So, that standard deviation picture is what you see here. What is obvious here is that if you look at the edges, right, that has a high value of standard deviation, not surprisingly because the heart is moving. So, we would expect a much larger standard deviation near the edges where the myocardium is, and that will help us actually localize the heart. So, we can do a standard deviation and threshold, and the regions of large standard deviation would correspond to the moving parts of the image. So, you see not all our organs are moving, there will be some slight distortion of the liver and all that because of the heartbeat, but that is not too significant. So, the highest standard deviation would correspond to the moving anatomy, which is the heart. So, that is the image that we get, the standard deviation image taken across different time points of the cardiac cycle or the cardiac phase. So, once we have that, then we can do an edge detector on the standard deviation image. Okay. We use a standard Canny edge detector. If you do not know what a Canny edge detector is, please you can search online, lot of literature on the subject. MATLAB has a Canny edge detector inbuilt. So, you can just look for that in the help and try it on some standard images that are provided. So, once we do this edge detection, we can then use, we have now you see that the circular objects are quite well defined when you do the edge detection. So, the edges are clearly defined. So, then you on top of that you do what is called a Huff transform. Okay. So, the Huff transform, again you have to look this up, we are not going to go through all of these techniques because it is not an image processing course. So, the Huff transform helps detect circles. So, this is the circular transform that you are using, it helps detect circles in images. Typically, if you have a black and white image like the one we have generated here, you can use it to automatically detect circles. Now, if you are wondering why that is so important, just think about how you would actually detect a circle in an image. It is actually a non-trivial problem to do. Okay. So, we will use the Huff transform to detect circle, and once we have the Huff transforms to detect the circle, then we can localize the left ventricle, the center of the left ventricle using some statistical techniques, and then have a box around it. That is the crop. So, we fix a standard box size and we take that out. Okay. So, that is the one, those are the images that we will use typically for training and testing and validation. Now, on the other hand, you can say that well the CNN is supposed to figure this all out by itself, that is also possible. If you do not want to do this crop pre-processing which involves localizing the left ventricle, you can actually feed the direct image, all the entire image directly to a CNN as input. It is just going to take, it is going to be slightly more difficult problem to solve because there is so much other confounding anatomy present. Okay. But in general you can do either of these approaches. The point I showed you this is also because you do not have to, just because there are these deep learning tools available to you, this is not you can use that to solve every problem, that is true, but then many of the conventional techniques that are out there, well studied, well documented and nicely programmed, you can use them to actually make the problem much simpler. So, what we have done by doing this cropping is to make the problem very simple. the sense that the CNN now does not actually have to localize the heart, right. In the sense now we know we are only giving it the beating heart as input, the other parameters are the ones that we will try to, the edges etc. would be the ones to focus on. Okay. Again yes, of course, if you do not want to do any of this, that is also fine, you can take the entire image, give that as input to the CNN. Also recall that when we did this, memory issues were also there, but now there are more powerful GPU cards and more memory available in them and RAM available. So, in fact, you can fit very large images and feed them as input to CNNs. Of course, training them is also much harder, you have to figure out the correct hyperparameters for the same. Okay. So, so what are we going to use? We are going to be using a CNN, no surprises there, because one of the powerful tools for image processing. So, the ones we just walk you through some of the ones we have already seen. So, this is a typical CNN that we talked about, where you have an input image or an RGB input image. In this case, we you can also have a series of a stack of images as input, that is also possible. Now, we have not looked at 3D CNN yet, I think I mentioned this in the when I talked about brain tumor segmentation, but in this case I think we are going to do plane by plane. So, this is the input image, then we have a bunch of feature maps extracted by the filters, and then come to a fully connected layer, and then the corresponding output categories. Okay. So, this is that typical CNN that you have all seen, just to refresh your memory. So, in this case also remember the problem that we want to solve is the one corresponding to semantic segmentation. So, we have to figure out the class that every pixel belongs to, namely the green, which is the myocardium or the muscles of the heart, especially around the left ventricle, the left ventricular cavity, LV cavity, this is the myocardium, and the right ventricle. Okay. These are the things that we want to label, okay, because they carry the most diagnostic information. Okay. So, this is so how we do that, we saw that by shifting to a fully convolutional neural networks CNN structure, then we can do semantic segmentation in one stroke. Basically the entire image through the one pass, all the pixels are predicted. Okay. So, that is accomplished by this is the encoding layer you can think of, and this is the decoding layer. The decoding layer uses bilinear interpolations or transposed up convolutions to increase the size of your feature maps, so that you are able to predict all the labels in one shot. And also the Inception architecture, wherein we are looking at receptive fields of different sizes in the same layer. So, typically in most of the networks you have seen till the Inception architecture, we fix the size of the filter kernel in every layer. Here every layer has a combination of different filter sizes based on the problem, for instance 1 cross 1 to 5 cross 5, that is the naive implementation. And of course, in order to make in order to make the computational more feasible, you also have the projection where we do the 1 cross 1 convolutions to reduce the size of each of the feature maps corresponding to different filter kernel sizes. Okay. So, these are the two examples here. For instance, one here this has 1 cross 1 to 3 cross 3 and 5 cross 5, this one has slightly larger filter kernels. Both of them are naive interpretations, except that this one what is missing here is the 1 cross 1 convolutions, which project them into lower dimensions, right, and then you can do the 3 cross 3. Okay. So, the other two concepts again that we are going to be using are the residual network and the DenseNet. So, the residual network, we saw that it improves your training, faster convergence, and you can go deeper by actually moving or adding feature maps from the previous layer into the successive layer. Like you can, let us say, the input to the previous layer x is then taken as the output and added to the output of the next layer. Okay. So, these skip connections you can do or in shortcuts, I mean whichever we want to call it. Okay. Is it, we call it shortcuts, right? This is short. So, we call these shortcuts. So, we call these shortcut connections. Okay. So, where we add them. So, here it is addition. So, in ResNet we usually add the feature maps from the from 2 layers below, okay, to the output. So, that helps in faster convergence, better learning, and it makes you do deeper networks. Another version of that is the DenseNet. Okay, here they go, they define a dense block which has several convolution layers. and one of the hyperparameters to the dense block is called the growth factor k equal to 3. In this case what happens is every convolution layer inside the dense block outputs exactly k feature maps, okay, and the output of the block is again concatenated to the input, that is what is shown here. So, you have L features as input, it goes through a dense block which has multiple layers including convolutional layers, and the output of the dense block is concatenated to the input. So, there this, so if this will be like k plus L features, okay. So, a layer, typically one convolutional layer inside a dense block. So, this is actually the blow up of a actually one convolutional layer inside a dense block. We have a batch norm layer in the activation function followed by 3×3 convolution. So, the prior to the convolution you have all these other operations which are also defined as layers. So, that is just one convolutional layer in dense block, okay. So, a dense block will have multiple such convolutional layers, okay, and each of them will output k feature maps, and you actually concatenate the input to that particular layer with the output, and it goes as again input to the next layer, okay. So, that is the idea behind dense blocks which we saw earlier. So, the architecture that we are going to look at is similar to the architecture which is reported in literature. It is called the 100, the paper is titled 100 layers theorem. Okay, so, it has about 100 convolutional layers. So, it has the kind of like a similar to a unit, but instead of just plain convolutions you have dense blocks, okay. So, the transition down blocks are again, so if you look at it, so there is an input where you do a bunch of 3×3 convolutions which, and the output of that goes to the dense block, and again the output of the dense block is concatenated, the C is the concatenation with the input, and there is a transition down layer which is again another dense block, except that has, that is the one that is blown up here, it has actually max pooling and 1×1 convolutions, okay, just to reduce the size of the feature maps, etc. So, after a couple of transition layers you have a bottleneck layer, again 1×1 convolutions, and then you do the transition up layers, right. So, that does 3×3 transposed convolutions, that is what. So, similar to a unit structure, and then you go all the way to the top, and when you are actually upsampling in your which is the decoding side, you also have these connections which is which will just concatenate, because this has the resolution intact. So, on the when you are upsampling, it is good to have the resolution back. So, that is done. This is the architecture that was reported in literature. So, we have made several changes to it. One of them very obvious change is the projection here. So, instead of directly concatenating, we just project it using 1×1 convolutions, and we just add it to the layer on the encoding side, okay. So, this is sorry, from the encoding side we add it to the decoding side, if you think of it that way, okay. So, these are, I mean, these are some of the changes. So, the idea is it is a unit kind of architecture, except that it has, instead of the plain convolutions, it has dense blocks, and we also have these connections going from the encoding side to the decoding side. There is a direct concatenation, here we project and then we add, okay. We also have an inception module at the beginning to consider different receptive field sizes and different resolutions, okay. The second aspect of the neural network is the loss function. So, we do the usual cross entropy loss function, okay, since we have about 3 classes, but it is weighted. The weight is obtained from the ground truth. So, for every image there is a corresponding ground truth here. As you can see, some of the rarer classes are weighted more, and then the classes that occur more frequently. So, for instance, if you look at the red regions here, the red regions, red line here is the weighting, this is the weight map. So, this what you are looking at here is the weight map. So, the red region here has a higher weight corresponding to the other regions, and if you look at the blue regions are weighted much lesser, this corresponds to a weight of 20, it is weight of 80. Of course, we have to normalize this so that it does not blow up. So, just to show that in scale we have shown it this way, okay. So, this is a rare region because we have a lot of overlap with the right ventricle here. So, that is difficult to segment. So, that edges are weighted more than the other edges. So, based on the pixel count, edge location, etc., each pixel is weighted differently. So, that is the weight map that goes into the loss function. Okay. The second aspect of it is that now since we are doing predicting all the pixel labels in one shot, one other way regularizing the output is by regularizing the loss function is by using what is called the dice coefficient. So, the dice coefficient what it measures, again this is the formula, is the intersection between the predicted mask and the ground truth mask. So, that corresponds to this region, that is marked true positive, right, divided by the cardinality of the mask plus the cardinality of the prediction. Okay. So, you can think of it as the fraction that you got right, okay, fraction of pixels that you predicted correctly. Okay. So, but then this if you want to actually use it inside a loss function, then you have to make it into a form that is differentiable, and that is what is given here. So, the P is your output score from your CNN. So, that is the posterior probability that is predicted by the CNN, and G is the ground truth corresponding to that. So, Xi is the pixel label. So, every pixel has its label corresponding probabilistic output and also its ground truth are given. So, summation over that divided by the normalizing factor. So, that is a differentiable loss function. Okay. So, when you write the total loss function, you have a hyperparameter lambda multiplying the cross entropy loss plus another hyperparameter multiplying 1 minus L dice. So, we want to minimize the loss function, that is done by maximizing L dice, right. So, if you think about it, if you want perfect prediction, then there should be an exact match between your, so loss L dice of 1, if you think about it, corresponds to a perfect match between your prediction and the ground truth. So, if you overlap them, you do not see any difference between them. So, that corresponds to 1. So, if you want to minimize that, the 1 minus L dice means then that would correspond to the correct segmentation, right, because the highest value of L dice corresponds to better and better segmentations typically. So, minimizing 1 minus L dice the same as maximizing L dice. Okay. And then we have L2 regularization, here W here are the weights. Okay. So, now we will now look at the architecture in much more detail and also look at how it is trained, etc., and interpretation of the results, so on and so forth. Mahendra will explain the rest of the architecture from here. So, what you see in this slide is the network architecture in slightly more detail. So, the input is basically a 128 cross 128 image where we cropped out the region corresponding to the cardiac anatomy and given that as input, and then we have the Inception module here, right, which outputs about 128 cross 128 cross 36, out of which there is 3 cross 3 convolutions output 12, 5 cross 5 convolution output 12 and 7 cross 7 convolutions output 12 feature maps. These are given as input to the dense block with k equal to 12, and it gives you about 24 feature maps as output. So, then you have about 128 cross 128 cross 60. Okay. The transition down layer reduces that to 64 cross 64 cross 60. So, we can do that again alternating between a dense block and a transition down block all the way to the bottom here where we get a 16 cross 16 maps, 144 of them. So, we have a bottleneck layer which outputs about 60 maps, and again from this is taken up by the transition up layer, which goes again all the way to the output segmentation map of size 128 cross 128 cross 1, and in between we have all these shortcuts we call them, which basically take the feature maps at the corresponding level. So, remember as we come down this side, this is the encoding side, the resolution starts to go down, and we here on this side we are trying to upsample. So, it will be though this to improve the upsampling, we take information from the encoding side. So, to and pass it to the decoding side, and that is done by projecting using a projection layer. So, we can project the 128 cross 128 cross 60 into one feature map and add it to the feature maps that come out of the transition up blocks. That is what happens in every layer typically. Okay. So, the optimizer we use Adam with a learning rate of 10 raised to minus 3. The weight initialization Hay normals weight initialization is used. We use a batch size of 16. So, mini batch size is 16 and about trained for about 200 epochs, and it is at about 400,000 parameters. We also have to augment the data by random flips. Flipping is you flip the image left right or right left, rotations, translations and some elastic deformations which are very small deformations. So, because cardiac anatomy we can't randomly deform, but these are deformations which we actually manually have to look at the range at which we can do. TensorFlow, this is programmed in TensorFlow, and TensorFlow has its own inbuilt routines for deformation, which are parameters that you can tune for deformations that are not too that will actually what do you call make it make it unphysical. So, you can't randomly deform the heart. So, remember that it is an anatomy we are looking at. So, within the confines of the problems that we will be able to deform the produce deformations. Okay. The intensity normalization, we use slice wise minimax normalization, that is for every slice it is minimized between 0 and up to the range is confined to 0 to 1. Okay, that is the way of doing it. After prediction, we do post processing. So, what does post processing do? It does largest connected component analysis. So, in MATLAB these are automated. So, please in MATLAB please look up connected component analysis. Okay. It comes under the topic of morphological image processing, you can look that up too. So, we do largest connected component and also hole filling, again morphological binary hole filling. So, what do you mean by that is, if you look at it, there is a nice prediction here, but if this is not correct. So, if we do this connected component analysis, what it does is to identify the large connected components, and we can place a threshold on it. This can be slightly arbitrary, that depends on your problem, and remove the small ones corresponding to every class. Okay. So, for every class we will do connected component analysis and remove the ones that are not meaningful, right. So, we expect the left ventricle to be in one piece and we take the largest piece possible, okay, if you think of it like that. And so, this is a post connected component analysis. We also do hole filling. So, for instance, this class is this is again a wrong classification. So, we have to fill that up with the correct classification, that is also accomplished using morphological hole filling. You can, again MATLAB has all of these enabled, so you can actually look that up also. I think Python and other like Python also has some of these morphological image processing tools also available.